Hey everybody, this is Larry. Hit the like button, hit the subscribe button. Let me know how you doing this problem. I'm gonna solve it live right about now. Okay, let's go. 793, pre-image size of factorial zeros function. Then f of x is equal to the number of zeros at the end of x factorial. For example, f of 3 is equal to, okay. Do we just find for example, okay, find how many non-negative integers x have the property that f sub x is equal to k. Okay. So you can do that. I think you can do it with a binary search. Basically, you do two binary search, one for the beginning and one for the end, or one for k and then one for k minus 1 or something like that, or k plus 1, and then just do a subtraction that way. I think that will allow me to do it. Of course, I'm skipping a little bit because I have a little bit of experience with the other part of it, which is how do you find the number of zeros in x factorial, and I will go over that now. So the thing to notice about x factorial is that x factorial is equal to 1 times 2 times 3 times dot 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 times x, right? Obviously. And what does it mean to have a 0 at the end of x factorial, or any number really, right? So let's say you have a number that's 10. Well, 10 is equal to 2 times 5, right? Let's say you have 100. Well, that's equal to 2 times 5 times, well, you could say 10 times 10, which is equal to 2 times 5 times 2 times 5, or 2 squared times 5 squared, right? And then now, let's say you have a less, more weird number, say 800, right? Is equal to 8 times 10 times 10. So that is also equal to, 8 times 2 over 2 squared times 5 squared. And the thing to notice is that the number of zeros is just the number of tens in the division, right? So yeah, f of x, f number of zeros in a number n is equal to the number of 10 in the divisors, right? Or like number of times you can divide by 10, something like that, right? And the number of times that you could divide by 10, as it turns out, is just the number of times you can divide by 2 times 5, right? So that's kind of the, an observation that you need for this problem. And then now let's go to x factorial, right? X factorial is equal to 1 times, this thing. And well, how many, and you could rephrase the problem as, well, now f of x factorial, f of x, is equal to the number of 2's and 5's in this problem, right? In this factorial, or sorry, in this multiplication, right? And what I mean by here is that, x factorial is also equal to 1 times 2 times 3 times 4, which is 2 times 2, times 5 times 6, which is 2 times 3, times 7, which is a prime number, times 8, which is 2 to the 2 cubed, times 3, and then times 10, which is 2 times 5, right? And in that case, you can see that the number, and then you just count up the number of 2's that appear in all the factorization, and the number of 5's, and then that will give us the answer, right? The minimum number of 2's and the 5's, because you need equal number of them to make 10, right? And then from this observation, the observation is that, well, if you look at the sequence, you're always going to have more 2's than 5's. So then the question becomes, how many times does 5 appear in the sequence? And well, 5 appears in the sequence every fifth number, which is on 5, on 10, in 15, on 20, and so forth, right? Except on 25, it actually, let's dot 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 this. On 25, it appears twice, which is 5 times 5, right? And then also on 50, it's also 2 times 5 times 5. So then now the number of zeros is that on every fifth number, you add 1 0. And then on every 25th number, you add 2 zeros, or 1 additional 0 more than you had before. And then on the 5 cubed, which is 125, on the 125th 5, we have a third 0. And then you kind of do that recursively to count the number of zeros, and that's how you count the number of zeros in X factorial. So that's something that I actually knew beforehand because I did this proof before. Some of it maybe even on stream, but that's how you would get, given a number X, that's how many K's you have. And then now we just have to come up with, right? We just have to come up with the number of zero. What is the number that will give you exactly, we use binary search to construct that. If we have a prefix sum of, so now let's say you have a prefix sum of how many zeros, or not a prefix sum, but let's say you have an array that has, f of 0 factorial has 0 zeros, f of 0 is equal to 0, f of 1 is equal to 0, and then dot dot dot, because they tell you in the solution. F of 4 is equal to 0, f of 5 is equal to 1, f of 6 is equal to also just 1, and then dot 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 all the way to f of 10 is equal to 2, and so forth, right? It should be equals to 3, and then 20 should be equals to 4. And the reason why there's no 5 is because on 25 it actually has 6, right? It jumps to 6 because what we talk about with the thing. And now from this point, all we have to do now is to do a binary search, because now you look at the sequence and you know that it is increasing, and because it's increasing, you could do a binary search for the answer that gives you this exact answer. But because 26 is also 6, and because it is factorial, it's going to keep doing the same until it goes to 30, and then it will go to 7. So you could do so actually so it's interesting, because initially I really thought that I would just do a binary search and then count, but it turns out that the answer can only be 2 things now, right? I don't know if it's obvious yet, but the answer is that because it only changes at the 5, then the answer will be 5. It is possible, because it doesn't change until the next number. And if it's not possible, then it will be 0. So now we have 2 of that, but we still have to figure out whether the exact number is possible. And from that, we can actually just maybe do something ad hoc. The binary search would still be fast enough, I believe, and you could apply for a more general problem. But for this particular one, what number is impossible? Well, 5 is impossible, and then what's 50 like? Well, 50, we do 35 is equal to 8, 40 is equal to 9, 45 is equal to 10, and 50 goes to 12, right? So the question is, well, what is k? K is up to 10 to the 9th, so that's gonna be big. And what numbers does it skip? Well, it skips 5, and then it skips 11. But Well, yeah, I think maybe if you're being clever, you can construct this in a way that allow us to do it. But I think I'm going to just go with binary search, and then the binary search will let us know whether it exists, because we just do a binary search for a number that has at least k zeros, and then we just see if it has that exact number of zeros. So basically, for example, in this sequence, we do a binary search for 5, or the first number that has at least 5, and then it will give us 25 ideally, and then we just run it one more time, and because it is not equal to 5, then we just return 0. Okay, so let's get that implemented. So let's first implement this f function, f of x. So it will give us, and let's just say for a given k. Yeah, no, this is fine actually. And as we said, we just want to return the number of zeros the number x has, and the number x has will be, let's just say, have a count, and then while x is greater than 0, count over x divided by 5, because it's every fifth one, and then x we divide it by 5, and then we go again, and then we return count at the very end. Okay, so that's the number of zeros. We could probably just for sanity sake, we could just test it for the first 100 numbers, just to print it out and then kind of prove it to ourselves a little bit, but I think this should be right. Yeah, so 0 up to 5, and then it changes at 25 and so forth. And yeah, so that feels good, that looks good. So then, yeah, now we do the binary search. So we start with a head is equal to 0, tail is equal to, so k could be 10 to the 9th. What does that say about upper bound? Well, k is going to be, could be possibly, maybe what, I don't know where it gets to, but okay, let's play around with this for a second then, right? I think it's important. You could just choose a big enough number and maybe that's okay, but let's just see how many zeros 1 billion have, right? This will help us kind of narrow it down a little bit. So 1 billion will give us this big number, which is 250 million, right? So this is for k is equal to 250 million. That means that we actually need a 64-bit int, because we need something like 6 billion maybe to approximate. Oh, no, 6 billion is too big. Now we're doing eccentric binary search, but 4 billion. So actually 4 billion works, which means that it fits in an unsigned int, but that's for simplicity's sake, we use an 64-bit int in your favorite language. And yeah, so in that case, we just, and I know that 4 billion is good, so let's just choose 5 billion. So that it's strictly bigger, right? So that we can't play around with it. But that's just the constraint for binary search. So now we write the binary search. Mid is equal to head plus tail over 2. And again, this is stuff that in your language would have to be a 64-bit int. In Python, these numbers get auto-promoted to a 64-bit int, so I don't have to do anything explicit, other than maybe taking a performance hit in theory. But you know, I'm not gonna worry about it, because when you need it, you need it. It's not worth worrying about. In this case, anyway. If you're using Python, it's already probably a little bit slow. So okay. So if this is at least k, so if we have at least k zeros, what does this mean, right? That means that, let's say we're at 25 and this has 5 zeros, then that means that the solution is in, that means that we want to look at the lower half, because we know that this is true, right? And conversely, if this is false, if this is smaller than 5, let's say we're 20, then we want to move the head to the next number, because we want to consider the big half. Okay, so yeah, if f of x is strictly less than, then we want to move head to the mid plus 1, else we want to move the tail to mid. And when they converge, that is good. And then now we know that head is the first element first x in which f of x is greater than or equal to k. But is it equal to k? If f of x is equal to k, we return 5. Otherwise, we return 0 because there's no k in that example then, right? Because in this condition, if the biggest the smallest number that's bigger than k is not k, then it doesn't exist in the sequence. So let's run this. Let's actually put in more answers, and we could put some big numbers, play around, and yeah, and let's see if the mix is okay. But x is not defined. Oops. Mid. In this case, I said f of x because I was talking about f of x, but the head matches this head, and the mid matches what we're binary searching for. In this case, yeah, I'm gonna take so by the pigeonhole principle, it seems like every fifth number at the very least cannot be true, I believe. So let me play around with at least getting an answer that gives me the 0 case. And we know that 11 is a 0, for example. This is really hard to see. I mean, I know that this is correct, but I want to... okay, so there's more zeros at the bottom. And we also know that 11 is a 0 case, so let's try that as well. Okay. Yeah, as expected, so now let's submit it. Cool. Yeah, so this is a fast solution because it uses binary search, and this takes log base 5 times, which is log of n in either case. So yeah, so that's the problem. It's a fun, hard problem. It is probably too hard for an interview because you need to make all these observations, which is kind of tricky. Like the code, you could say that it is 20 lines of code, so it's easy, but definitely for an interview, this is ridiculous a little bit because you have to make one observation. Well, okay, this is not an observation, but you have to make an observation that the number of zeros is equal to 2 times 5, and then you have to make an observation that you only care about the 5, though strictly speaking you don't need to. You could just write 2 functions and then take the min of that, but this will be true. And then you have to notice that x factorial has this increasing number of 2's or 5's or 2 and 5's property, and then from that you could binary search from that, and then you have to notice that that in this pattern, this can it's each case could either be a 5 or a 0, and that it is a 0 if it doesn't have the number that is exactly true, which you have to do a binary search and make sure that this case holds, right? And there's so much magic constant in this. With the magic constant comes from math and what we did before, but and while it's possible, and for me, you see me do it live, and I haven't seen this problem before, but I do know these properties before, so I was able to prove, like I've always spent time proving it before. So while it looks like I'm solving this live, and I am solving this live, but I've spent the time in a previous life, right? So it's not like I did this out of nowhere, and that allows the practice mixed the speed in this case. But definitely on an interview, I would not recommend it, or I would not expect to have that level of knowledge on mathy stuff. If this was more, if there was more algorithm and data structure, then maybe it's okay. But on this, it's just pure understanding math, and I don't agree with that. For competitive programming, it's fun, and it is expected that you come up with these kind of things, so maybe that's okay. But definitely for interview, this is ridiculous, and it is hard. Even if the components of binary search, I would say it's a basic technique, and you definitely should practice it. And yeah, definitely practice it, binary search. But this problem may not be that problem that you practice, because it requires a lot of stuff that you have to play around with, and it'll take you a long time unless you already have done it before. Parts of the problem, if not the entire problem. Anyway, That's all